Welcome to AMS on the Air. I'm Dakota Smith.
I'm Jeff Rosenfeld.
And I am Irene Sands. We're here to podcast all things weather, water, and climate. Fire can cycle carbon and result in more carbon in the atmosphere. Smoke, black carbon, and organic carbon can also circulate and land on the Greenland ice sheet. And when it does, it can force ice and snow to melt more quickly.
Dakota, one of the things that you do is you're involved in an area of research where you're connected to so many different aspects of the community, and there's a lot of interdisciplinarity that goes on. And I don't know, has there ever been anything that sort of surprised you how what you did was related to their field, or the strange combinations of people who get together because of what you're doing or what your group is doing?
I think one thing that I started learning as I was an undergrad and then in grad school was how many different professions and fields were impacted by weather and in some aspects climate. And when I saw all my friends, doing their work and becoming, expanding in their careers and getting jobs, I realized that so many of their fields were impacted by weather, but they had nothing to do with either the environment or weather in general.
I think as a scientist, we notice that more than the public. I mean, when I've done videos and I explain, the water, just the water cycle. If you look at the water cycle, everything we do with our water, from drinking it to taking a shower to wasting it to everything we do with the shower, with the water, it's just, that's our life. And it's all connected.
Yeah, I really feel like the interconnectedness of the world has become more and more important to us as we start thinking more and more about how to deal with climate change, or even just day-to-day pollution issues that may or may not affect climate long-term, but are the questions of how we deal with waste or how we clean up the air. And this is one of the great things that came up in an interview we just had at the annual meeting in Phoenix this year with Amber Soja of the National Institute of Aerospace. She's an expert in fire, and in particular in fire in Siberia, and that just sounds so remote to me. But when we started talking, she just opened up this subject, from the dirt under your feet to the trees overhead to high in the atmosphere to the oceans to climate change, all across the world, all connected together in ways that I hadn't thought of before. So I think it's really worth taking a listen. If you think that weather and climate mean that we're all connected to one another, you will understand it at a far deeper level listening to Amber talk about it.
In general, I look at fire and feedbacks to climate change. So any work that I do has to do with fire. I'm not only ground-based, but I think from the satellite in air quality. So I'm interdisciplinary, and that's something that's different about me, is that I try to connect all the pieces, and I see them as being important to connect. I don't do any work that doesn't have the word fire in the word and the work. So with We Can, what's interesting is that they're looking at the chemistry from aircraft, and they're also looking at the models. But what people haven't done is they haven't connected it to the ground, to the fuels on the ground, and to the fire weather that controls how dry the fuels are and how available they are to burn. So you could have different ecosystems that hold different amounts of carbon, and then you use species-specific emissions to get the species that are, and gases and aerosols that are important to air quality. The ecosystems hold different amounts of carbon, but even if you have the same ecosystem that holds the same amount of carbon, depending on how dry the fuels are, that's controlled by weather, longer-term weather, which is a combination of temperature, noon-to-noon precipitation, wind speed, and relative humidity. And then it adds up over days. So if you think about it, it only takes, a few hours to dry a leaf or lichen, but it takes longer to dry the deeper duff or the larger diameter type fuels. So if you have a drought or a real dry season and you get an ignition, that's going to end up being a bigger fire that consumes more fuel. So even in the same ecosystem that has different types, that has the same amount of fuel, you'll have different types of emission because of the fire weather. And it's just something that hasn't been connected. Everybody is talking from a different place. And it's hard to think outside your field. So if you're a satellite person and you're looking down, you're thinking of fire detections and fire rated power, and let me go ahead and get my emissions. But you're not thinking about the differences in these ecosystems and what's happening on the ground. And the atmosphere is fueled from below, from my perspective. But from an atmospheric perspective looking down, they would say that the atmosphere controls the ground, and they're really connected.
What would you say is your perspective? I mean, obviously climate is a big part of how you're looking at it, but it seems like a biospheric perspective is sort of where you started environmental studies, or how did you get into the point where fire became a focus of your interest?
So I went to school, or back to school, because I wanted to understand more of what was going on. And as I understood that temperatures were increasing and that climate is warming, I was interested in carbon, the amount of carbon on the ground. So that my advisor said, if you're interested in carbon, it's in the boreal forest. And most of the boreal forest is in Siberia. So my actual area of expertise is in Siberia. And that's where most of my field work has been done, in Siberia, some in Canada as well, but mostly in Siberia, which is 3/4 of the boreal forest. So it's very important. And it's a shame that for political reasons, we really can't go there anymore, because it's this massive northern continent that we don't have scientific access to, and they really need us there. They really need our insight. Why do you say they need us there? Because science can be inhibited there, and in Siberia.
Is there a real vibrant scientific community looking at the boreal forest in Siberia or in Russia or anywhere that might have
if it
resources?
would be, it's funding. So if it were funding, there are people that are interested.
Yeah.
Yeah, fire can set succession in a different direction.
It's interesting.
Fire cycles carbon. Fire can cycle carbon and result in more carbon in the atmosphere, because a lot of the peatlands, whether they are in the tropics or in the boreal forest, they've been stored for millennia, and it's going to take centuries and millennia to get it back, or it doesn't come back.
Mm-hmm. And that carbon goes up into the air.
Exactly.
Now this is another thing. Some fires burn particularly hot, some don't. What happens to that carbon? Does it go high in the atmosphere and stay a little longer, or does it end up in the oceans fairly quickly, or where is it going?
For the larger fires, and some of the fires that were the car fire, for instance, that was detected by the We Can campaign, there were several pyro-CBs. And pyro-CBs can inject through the tropopause into the stratosphere, where they have an incredibly long lifetime, similar to volcanic activity.
So the height of the plume, again, is another factor, not just the ecology of the forest that's burning, but then the dynamics of the fire itself.
Yes.
That's another factor you've got to... You're starting to pile up issues here, making it very difficult to do your job.
It's a circle. It's a feedback.
But
and you're right. Yeah, you have to have fuel. It has to be dry enough to burn. You have to have the right weather conditions, and then the fire plume, the smoke plume, can pop up through the tropopause.
How often do you get pyrocumulus? Is or pyro-CBs? It's a term that is now something everybody talks about, but I don't remember people talking about it so much, say, a couple decades ago. I mean,
it's true.
It heard it, but no one really talked about it. But why is it now
Because we have the satellite data that's available to prove that it's really happening. It was Mike Fromm, who is here now and has given talks, Mike Fromm, that came up with the words pyro-CB, pyrocumulonimbus, pyro-CUs, and he actually has a little talk, webmail now that we all get on, because you can kind of predict when they might occur. So there's a whole kinds of chatter. But in the beginning, there were only so many satellites, and he said, hey, there's this thing happening, and I think these fire plumes are popping up through the tropopause into the stratosphere. And some people said, wow, that's pretty interesting, and other people said, oh, that's a bunch of malarkey. He was very much poo-pooed. And then as we started to get more satellite data, more observations, more ways of looking at things, and he just kept on fighting that battle until now it's accepted. And now in his latest research, he is the person with David Peterson, who's a younger, tall guy. They have shown that the latest pyro-CBs in BC, British Columbia, this past year, they were equivalent to volcanic activity. And then there's a lot of pyro-CBs.
Equivalent in what terms?
In terms of the mass injected into the stratosphere and the time it stays in the stratosphere and goes around in a circle. Now, radiative effects may be different, but in terms of mass.
It's not sulfur so much.
It's not sulfur.
But it's still a big effect.
Yeah.
That's pretty incredible.
It is incredible.
Cumulonimbus as a volcano.
And there's a lot more of them than had been originally thought.
And
he's even gone back in time and said, everybody, they would find aerosols in the stratosphere and they said, oh, we must have missed a volcano. And he has connected fires and said, you didn't miss a volcano, this was actually a fire.
Wow.
So he's gone back in time.
So when you're tracing back in time, when he's doing that, what is he looking at? What signature is he looking at that?
He puts together multiple types of information. Some would be from the ground that people report that because we know when there's big fires. It doesn't matter how remote they are. We know about the big ones.
Yeah.
And there is aerosol signatures that you can see in different satellite data that he uses. It used to be TOMS, now he uses OMI. Mm-hmm. So
these are ozone.
Yes.
Yeah.
Yeah, and you can see the signatures. Of
it kind of reminds me of the days when a lot of the upper air research was tracing the signature of a nuclear test and going back. It's kind of retracing steps to figure out where and when the test was, then probably correlating with geophysical activity in the ground as well. But finally, that's interesting.
It is interesting, isn't it?
Yeah,
we can trace a lot back because of how we've changed the environment.
Your research now is looking at a number of different things. What are you trying to learn to help sort of get a better handle on what's going to happen with changing fire regimes, or what could maybe be done to not change things, if that were even possible? What kinds of findings are you getting out of research, and what are you looking for as part of this problem?
So my role with WeCan is to provide information that they might not otherwise have. So to provide information that chemists and modelers don't have that relates the atmosphere to the ground. So that's my goal for WeCan and for upcoming FireXAQ. In my research, I do look at patterns of fire regime change that is motivated by climate. And the reason for this is it is predicted that fire regimes and severity and the amount of area burned will increase under current climate change scenarios. So if you know this is supposed to happen and you know where it's supposed to happen, we have satellite data where we can monitor these regions. So one area of research is to say, okay, is it changing? And the answer there is yes, and that is published. It seems like another step would go into the temperate forest and see if you see changes as much as you can there. It's a little bit more complicated in temperate regions because there are more people, and we've moved into the WUI, or the wildland-urban interface. Another area of research that I see is key to interdisciplinary connections is looking at smoke plume height. And we now have space-based LiDAR, Calliope on Calypso, and you can take a vertical slice through the atmosphere and see how high plumes are and see their vertical extent through the atmosphere. And we don't do a good job of placing smoke in the atmosphere in models, and we're getting better, but we need to verify, validate, figure out what type of smoke, how high smoke goes depending on ecosystem and fire weather. And there's a lot of connections we haven't had because we didn't have this type of data available statistically before. And the reason that's important is if you don't get the height in the atmosphere right, you don't get the transport right. It's because air higher up in the atmosphere goes faster. And if you don't get the height right, you don't get the transport, and you don't get the connections between to where it comes down. So smoke is a cloud condensation nuclei, so that will change precipitation and inhibit precipitation in the near field. Smoke, black carbon, and organic carbon can also circulate and land on the Greenland ice sheet, which it has. And when it does, it can force ice and snow to melt more quickly than it would otherwise. Now, if it's covered with snow, immediately the deal is done. They'll beat us the same. There's been no change. So you're going to need that perfect scenario. But it can cause decreasing of ice and snow more quickly than it would otherwise. And that would be the climate feedback. Smoke itself changes albedo, and which can be positive and negative feedbacks to the climate system. So all of this is important.
So we've got smoke affecting the precipitation and water cycle. Smoke, therefore, also having more to do with climate, just in that secondary effect of not only its own interplay with solar radiation, but then what aerosols come as a result, or water turning into clouds.
Yeah.
But then you've also got the melting of the ice sheets, depending on whether they're sooty on top or not, I guess.
So, because black carbon doesn't dissolve readily, as you melt, if you do get melting, you could possibly melt down to another layer that has more black carbon and more black carbon. That's
I assume there are ages or eras when there were large deposits.
Yes.
Yeah. And then...
which is a very complicated subject, actually.
Good.
I was working... I was on a project, a Greenland ice sheet project, and my team members were on the Greenland ice sheet, and they took ice cores, and they found this deposit that was pretty large. It was extremely large, and so my job was to find out where it came from, what fires could we attribute this layer of black carbon, this biomass burning signature. And it turns out that it wasn't the biggest fires. A lot of the biggest fires and a lot of the dominant transport path is underneath the ice sheet. That one seems to be the dominant transport path. And you would think that black carbon is deposited for all these big, huge fires. But it turns out that there were some medium large fires burning in Canada, and there was a low pressure system that picked the smoke up and carried it up and dumped it on the Greenland ice sheet.
So it was just a sort of a fluke, or a good sense of timing for the fact.
It has to be a good sense of timing. It was a good sense of timing. And the reason that's important is everybody thinks that when you have all this carbon on the Greenland ice sheet, it was because it was large fires. Well, that's maybe not the case. So it's a different way to look at it. It's like,
yeah.
And often when people look at ice cores, because there's a lot of carbon dropped in one place, if it isn't other ice cores around the world, they'll think, well, that wasn't a big fire year. But that might not be the right way to think about it. It still might have been. It's just that the transport path for this case just went to one place. Mm-hmm. So it's a different, we hadn't been thinking of it like that before.
One other factor then I'm wondering about is, does the deposition of these aerosols ultimately, you're going to affect the ocean, because the ocean is most of the planet, right? So if there's a fire and the plume happens to head out over the ocean and that stuff falls out because it's not, say, in the stratosphere or where it might live a little longer, does that affect biological production in the ocean at all, or does it have any other effects?
I would imagine that it would. I would imagine that the micronutrients in smoke would definitely affect the ocean's primary productivity. And I've seen some studies that have shown that. There's a lot of micronutrients that come off of the fires burning in Africa and dust in the Sahara-Sahel. So we have all these micronutrients, and they're transported towards Brazil. And as they drop off, you can see higher primary productivity in the oceans, becoming less and less and less. And it turns out there are some studies that have shown that you need these micronutrients in Brazil from these fires. They can be traced from Africa to Brazil. And without these micronutrients that are rained out in Brazil, you would not have the rainforest, because there aren't new nutrients there. So in the large geologic time frame, the tropics and the tropical forest in Brazil would not exist without the micronutrients from fire and dust from Sahara-Sahel and Africa.
All right, now I'm like, okay, I have one more question. It's like, is there something you don't have to know to study fire? It seems like everything in the world ultimately connects to this sort of cycle of impacts and, feedbacks. Is there anything in this field that's like, well, I don't need to know about that because I study fire?
I am interdisciplinary, and I tend to think that way.
I don't think we'll ever look at fire quite the same way,
Yay!
knowing all of these things. Again, now it's a new thing.
It's a big cycle. Which is why it's so interesting. So if you're interested in climate and you're interested in carbon and how it's cycled, fire's the key. Fire's the key. Fed by weather and climate, and weather and climate determines what the ecosystem will be as well. Weather on a larger scale. And then it feeds right back, almost like the Gaia principle that...
Mm-hmm. Yeah, Gaia, Paya, whatever. I appreciate it very much, because you've explained quite a bit.
Oh, good. This is fun. This was fun.
So that was our interview with Amber Soja, and I just have to say I'm really grateful to her for the way she pulled together so many different threads of the story and really opened my mind, at least, to what fire, ecology, climate change, what that's really all about, which, as she puts it, basically, it's about everything all at once.
If you have any comments, questions, interview suggestions, make sure to write us on social media. You can search us on Twitter, Facebook, Instagram, and also make sure to subscribe to our podcast using your favorite player.
For Jeff, Irene, and myself, thank you so much for listening, and we'll be back in your podcast feeds very soon. Happy weather, happy water, happy climate.